Thank you very much. First of all, I'd like to thank Sergei and Natasha for inviting me to such a nice conference again. In my talk, I'll discuss photoinduced phase transitions and optical nonlinearities in simple Mott insulators. This is the content of my talk. First, I'll introduce the far-field 1D and 2D Mott insulators and the overview of their optical responses. Next, I will discuss photoinduced Mott insulator to metal transitions. After that, I will talk about terahertz electric field induced phase transitions. And finally, I will present recent studies on flock states formed by a mid-infrared electric field. As you know, the photoinduced phase transitions of correlated electron materials have attracted much attention. In those materials, photoexcited states change surrounding electron and spin systems through strong electron-electron interactions, which may give rise to ultrafast photoinduced phase transitions. So far, various phenomena have been discovered, such as the photoinduced insulator to metal transition, anti-ferromagnetic to ferromagnetic transition, and para-electric to ferroelectric transitions. Those phenomena are attracting interest as central research subject in non-equilibrium quantum physics, a new field of condensed matter, and also as possible mechanisms for ultra-fast optical switching devices. This insulator to metal transition is the most typical photoinduced transition in correlated electron materials. As early stage works of photoinduced insulator metal transitions, the studies of perovskite manganite and VO2 are well known. In those materials, insulator metal transitions are induced via photoinduced melting over low temperature ordered phase, such as the charge order insulator phase in manganite and the Pyrrhus insulator phase in VO2. So far, various phenomena have been discovered along this strategy. Those phenomena involve charge, spin, lattice, and orbital degrees of freedom, so they are very interesting. But their dynamics are sometimes complicated and depend on specific features on each material. Here, I will focus on far-field Mott insulators, which have simpler electronic structures and are hardly affected by lattice degree of freedom. This is a schematic of a system with one electron per site. Since two electrons can occupy on each orbital, electrons are free to move around, and the system should be a metal. However, if a large on-site Coulomb repulsion works between two electrons on the same site, electrons are localized on each site, and the system becomes a Mott insulator. In this case, electron spins arrange anti-ferromagnetically like this. This half-field Mott insulator is the most fundamentally insulating state in correlated electron systems, so it is a good target to study optical responses in quantum many-body system consisting of strongly interacting electrons from both experimental and theoretical viewpoints. Furthermore, some Mott insulators show novel responses to light and electric field, such as ultrafast metallization and large optical nonlinearity. Here we show the far-field 1D and 2D Mott insulators covered in my talk. They include various materials, such as organic molecular compounds, halogen-bridged nickel compounds, and cuprate Mott insulators. They show a clear Mott gap in the absorption spectrum. This is a schematic diagram of the responses of far-field Mott insulators to light and electric field. The horizontal axis is the photoenergy of the pump light, and the vertical axis is the electric field amplitude. Early studies demonstrated the nonlinear DC transport, a large third-order optical nonlinearity in a transparent region, and the ultrafast photoinduced Mott insulator to metal transition by photocarrier generation. Recent developments of laser technology enabled the ultrafast pump flow measurement with the time resolution shorter than 10 frames per second in the visible to near infrared region, and the generations of an interstellar pulse and a phase-stable mid-infrared pulse, which made possible sub-cycle spectroscopy. These optical techniques are leading to the detections of ultra-fast charge and spin dynamics in the photo-induced insulator to metal transition, the terahertz nonlinear optics, terahertz electric field-induced quantum tunneling and charge transfer, resulting in the phase transition, and the detections of Flock state and Flock engineering. We have performed some studies, some related studies, which are shown here. In my talk, I'd like to discuss several novel phenomena on this diagram in 1D and 2D Mott insulators. The first topic is the photo-induced Mott insulator to metal transitions. This is a electric state change expected upon photoexcitation in half-filled Mott insulators. By a photoexcitation, the electrons are excited to other sites like this, and doublons and holons, which correspond to the electron and hole carriers in semiconductors, are generated like this. In this situation, electrons can move into holes without an effect of Coulomb repulsion, and the excited electrons can also move. So, if a number of carriers are generated at once by a laser pulse, the original electron order may be melted, and the system may be converted to a metal. Since this metallization does not change the crystal structure, but change only the electron order, it may occur very fast and return to the original state in the time scale of picosecond. Here, I'd like to review the coupling of charge and spin degrees of freedom in Mott insulators. When a hole carrier is introduced in a 2D Mott insulator with large U, it moves by disturbing the anti-ferromagnetic spin arrangement like this and like this. So, charge dynamics is coupled to the spin dynamics, and the carrier cannot freely move. As a result, the introduction of carriers produce mid-gap absorption, that is the incoherent part. Further carrier doping gives rise to the metallic state. However, the drilled weight is small as compared to the incoherent part. The electron doping is in the same situation. These features were indeed observed in the chemical carrier doping in cuprates. In the case of the 1D Mott insulator with large U, the carrier dynamics is considerably changed. For example, by a photoexcitation, a doublon-holon pair is generated, which moves without disturbing the anti-ferromagnetic spin background. So, the charge dynamics is decoupled from the spin dynamics, and the carrier can freely move. This feature is called spin charge separation. So, by a photocarrier doping, the spectral weight of the gap transition is expected to be transferred to the Drude component, irrespective of carrier density. Keeping these features in mind, we will discuss the previous result of 1D Mott insulators. The studied material is ET-F2TCNQ organic compound. In this compound, an electron is transferred from ET to F2TCNQ. Each F2TCNQ molecule is almost isolated, and the overlap of pi orbitals exists only between the neighboring ET molecules. So, 1D half-filled band of ET stacks dominates its electric property. Because of large on-site Coulomb repulsion U on ET, this compound is a half-filled 1D Mott insulator. In the absorption spectrum, a sharp peak due to the Mott gap transition is observed at 0.7 eV. In this figure, the solid line shows the original reflectivity spectrum, and color marks show the photoinduced reflectivity changes delta R by the 1.55 eV excitation. The upper part shows a strong excitation case with the excitation photon density of 0.1 photon per site, and the lower panel shows the weak excitation case with 0.003 photon per site. In both cases, spectral weight of the gap transition is transferred to the inner gap region. By the strong excitation, the decrease of the reflectivity reaches 18%, which is comparable to the original reflectivity peak. So, the optical gap almost disappears and photo-induced Mott transition occurs. By the weak excitation, delta R also monotonically increases with decrease of energy, and the spectral weight exists in the lower energy region as compared to the strong excitation case. This suggests a simple delayed response. To clarify this feature, we focus on the time dependence of the infrared spectra, which are expanded here. As shown by the arrows, the crossing positions for delta R equals 0 shift to the lower energy with time. Such a feature can be explained by the decrease of the carrier density with time in a simple delayed response. In fact, these spectra are almost reproduced by a simple delayed model as shown by the block lines. This demonstrates that the spin charge separation actually stands in this response. Similar simple delayed responses are observed in other 1D systems such as bromine bridge nickel chain compound and palladium chain compound. Let's move on to the Mott insulator. Here we focus on this compound, neodymium kappa-O4, which is a parent compound of an electron-doped superconducting couplet and is a typical 2D Mott insulator. In this figure, this solid line shows the optical density spectrum, that is the absorption spectrum, and color marks show the photo-induced absorption changes, delta OD. The time resolution is about 200 femtoseconds. The spectra are complicated as compared to those observed in 1D Mott insulators. Here we expanded the infrared spectra in a normalized scale. Just after the photoirradiation, absorption monotonically increases with decrease of energy, showing a metallic behavior. This suggests that the insulator metal transition occurs. However, this Drude-like response decays very fast, and after a few picoseconds, the spectrum is dominated by the mid-gap absorptions, which can be assigned to the residual doublons and holons, localized by the charge spin coupling. In the near infrared region, peak structure is observed, which is attributable to the heating of the system, since this spectrum is very similar to the absorption change due to the temperature increase shown by the gray line. Detailed analysis of time evolutions of absorption changes at these three probe energies revealed that the, de the decay of the metallic state occurs very fast. That is much faster than the time resolution. And the residual holons and doublons also decay very fast. Its decay time is about 300 femseconds. What is the mechanism of this ultrafast decay? Several theoretical studies suggested that the fast recombination of a doublon holon pair in this region is possible via the energy transfer to the spin systems. In this compound, the exchange interaction J is about 0.13 eV, and magnon dispersion exceeds 0.3 eV. So a magnon is a good energy receiver. Next important issue is to clarify the photoinduced metallization and relaxation processes in this initial time region. In this compound, the time scale of the transfer energy is about 10 femseconds, and that of J is about 30 femseconds. So, in this process, the charge spin coupling would be also important. So, it is important to detect the charge and spin dynamics. To detect them, the time resolution of 10 femseconds is necessary. Considering this point, we constructed the reflection type from probe system using 7 femsecond pulses and performed the experiment with a time resolution of 10 femseconds. A 7 femsecond pulse has a broad spectrum which is located inside the Mott gap transition. By a photo excitation, the spectral weight of the Mott gap transition should be transferred to the inner gap region. So, by measuring the time evolutions of the bridging signals at the Mott gap transition, we will be able to detect the dynamics of both metallic state and mid-gap state. This figure shows the time evolutions of the bridging signals of the Mott gap transition for various excitation photon densities. This is a response function corresponding to the time resolution. A finite signal is observed before the time origin, which is attributable to the perturbed free induction decay of probe pulse induced polarization. This response is not related to the carrier dynamics, so I will not discuss them here. With increase of the excitation photon density, the ultrafast deep structure shown by the arrows are enhanced like this. Considering the result with the 200 femsecond time resolution, this ultrafast response is attributable to the photoinduced metallic state and the residual slow component to the mid-gap state. Here we plotted the typical time evolutions of the reflectivity for low and high excitation density. For the low excitation density, we can see the rapid decrease of the reflectivity due to the hot carrier generations and the subsequent decrease of the reflectivity labeled as B. By the fitting analysis, we evaluated that time constant of this process B to be about 20 femseconds. This time constant is much faster than the time scale of holons, that is 60 femseconds, and that is comparable to the time scale of spin, that is 30 femseconds. So this process can be assigned to the spin relaxation processes of carriers, that is the magnetic polar formation, via the weakening of the anti-ferromagnetic spin arrangement like this. For the high excitation density, we also extracted the ultrafast component by the fitting analysis, which is shown here. Its decay time is about 10 femseconds. This time is attributable to the decay time of metallic state. Here we plotted this decay time as a function of the excitation photon density. The decrease in the decay time with increase of the excitation density is characteristic of OJ recombination of carriers, where double hollow pair recombines by transferring its energy to other carriers. Such efficient carrier scattering processes would be specific to correlated electron systems. Okay, this is the overall photo-induced metallization and relaxation dynamics. By the weak excitation, the metallic state is hardly observed. By the strong excitation, the metallic state is formed, but it decays very fast via the OJ recombination processes, and the residual doublons and holons are relaxed as magnetic polons via the weakening of the anti-ferromagnetic spin arrangement like this. And finally, they recombine with 300 femseconds via transferring energies to spin excitations.
And the first transition is from the first panel to the right is response to what exactly?
Excitation is performed beyond the Mott gap. So, but when the excitation density is very small, the metallic state can be formed. Okay, so the small number of carriers cannot freely move. But in that case, the carrier number is very high. So in that case, the metallic response is observed. Okay. Next, I will discuss the terahertz electric field-induced phase transitions. More than 10 years ago, a method to generate an intense terahertz pulse called pulse front tilting method was established, and it became possible to generate a nearly monocyclic terahertz pulse with a period of 1 picosecond and amplitude much larger than 100 kilovolt per centimeter. The unique feature of this pulse is that a strong electric field can be applied in a specific direction like this. Furthermore, by using a probe pulse with a time width of 100 femseconds, electronic state changes along the electromagnetic field can be detected. This method is called subcycle spectroscopy. A lot of attempts to control physical properties using a strong terahertz pulse have been reported so far. In those studies, it was able to control, for example, phonons, polarizations, carrier number in semiconductors, magnons and electromagnons, superconducting order parameter, and so on. Attempts to drive phase transition have also been reported. A typical example is the study on VO2. In this study, an insulator to metal transition was induced by a terahertz electric field enhanced to about 2 megavolts per centimeter in a material resonator. However, this transition originated from the heating due to the accelerations of carriers by the electric field and was accompanied with large structural changes. In fact, the transition dynamics is much slower than 1 picosecond. To achieve an ultrafast phase control in a sub-picosecond timescale, it is a good way to focus on electronic phase transitions without large structural changes. Considering this, we focus on a Mott insulator again. The previous theoretical studies suggested that an application of a strong electric field inclines both the upper Hubbard band and lower Hubbard band, and carriers can be generated through quantum tunneling processes. We can expect that such carrier generations gives rise to the conversion to the metal. The theory also predicted that the electric field necessary to generate carriers is very high. It is 3 megavolt per centimeter in 1D Mott insulator ETF2TGNQ mentioned before, and increases with increase of the Mott gap energy. So, to drive a transition by a lower electric field, a narrow gap Mott insulator is advantageous. Considering this point, we focus on this organic molecular compound called kappa ET2X. In this compound, ET molecules and anion X molecules form layer structures like this. This is a projection of ET layer on this plane. A unit is an ET dimer. The nominal balance of each ET is plus 0.5, and each dimer has one hole. So, 2D half-filled band is formed in this compound. This is a schematic phase diagram of ET2X family. The horizontal axis is the effective band width, which can be controlled by the choice of X. This is a metal Mott insulator boundary. Here we focus on this compound with X equals Cu NCN to Br. A bulk crystal of this compound is a metal at low temperatures. In the absorption spectrum, no gap is observed at 10 K. On the other hand, a thin single crystal on a diamond substrate becomes a Mott insulator at low temperatures because of the negative pressure from the diamond substrate. So, in the absorption spectrum, a clear gap, Mott gap is observed at 30 millieV at 10 K. So we perform the terahertz optical absorption probe spectroscopy on this sample. This is terahertz electric field waveform, and this is its spectrum. This sample is completely transparent to the terahertz pulse, and no carriers are excited beyond the gap. This figure shows the time evolutions of the absorption changes for various probe energies. The amplitude is 180 kilovolts per centimeter. The signal rises very fast and reaches the maxima at 0.7 picosecond and decays with a few picoseconds. This is the delta OD spectrum at 0.7 picosecond, which increases with degrees of energy, showing a metallic behavior. In fact, this spectrum is almost equal to the differential absorption spectrum between metal and Mott insulator, shown by the broken line. This suggests that the electric field induced Mott insulator to metal transition occurs. To clarify the transition mechanism, we next investigated the electric field dependence. This figure shows time evolutions of the absorption changes for various electric field amplitude at 0.12 eV, which can be a measure of the carrier density. This is the electric field dependence of delta OD at 0 picosecond, this point. This shows threshold behavior. The theory predicted that the probability of quantum tunneling processes can be expressed by this exponential formula. The result is well reproduced by this formula. This demonstrates that the insulator metal transition is driven by carrier generations via the quantum tunneling mechanism. To investigate the dynamics in more detail, we also plotted tilde OD at 0.7 picosecond, at which the signals take maxima. This is a logarithmic plot.
And what is special at 147 kilobyte? Why you have three oscillations?
Yeah.
On the previous slide. Yeah, this 147 kilovolt, but
No.
It was.
Yes. We
Actually, it's different from the red and others. That you have the on the blue line, you have the third one. Second from the
are you asking about this this oscillation?
What is the reason? Because neither up nor down you don't have this thing.
This oscillation? No.
Yeah.
This oscillation is a different issue. That after the photoinduced insulator metal transition, the metallic state is further stabilized by the molecular displacement. So, but the time scale of the molecular displacement is about, the period is about 1 picosecond or something like that. So the insulator metal transition occurs in the faster time scale. Okay. Let me discuss just after this slide. So this is a logarithmic plot, and in the weak electric field region, the Mott transition seems to take a finite time. To clarify this feature, we analyze the time evolutions of the absorption changes at this electric field and evaluated the rise time to be 0.13 picosecond. You can consider this rise time is a characteristic time of the Mott transition. It is reasonable to consider compare this time constant with the transfer energies. The interdimer transfer energies of this compound are shown here, and the smaller transfer energy, 33 millieV, correspond to 0.12 picosecond, which is comparable to this rise time. This suggests that the electronic state change in the Mott transition takes a finite time. They are determined by the transfer energy. Okay, so this rise time is 0.13 picosecond. This is the electronic response, and after that, the molecular displacement occurs coherently. But that period is about 1 picosecond. So the initial process is purely electronic. Okay, more recently, an organic nonlinear optical crystal called DSTMS is also used to generate more intense terahertz pulse. This technique was developed by Howley Group. Using this crystal, we also produced the strong terahertz pulse with an electric field amplitude larger than 3 megavolts per centimeter. And using this terahertz pulse, we investigated the metallization of a Mott insulator with a larger Mott gap. The studied material is the one Mott insulator ETF2CCNQ mentioned before. The Mott gap is 0.7 eV, and by the excitation with the terahertz pulse having the amplitude of 2.8 megavolts per centimeter, the clear Drude responses are observed like this. This indicates that the electric field induced insulator metal transition occurs. These results suggest that a terahertz pulse is a strong light source to generate carriers in semiconductors and insulators with a larger optical gap. Okay, let's go back to the kappa ET2X compound. The previous theoretical studies and dielectric measurement suggested that these two compounds, Mott insulator compounds, far from the metal Mott insulator boundary, includes an instability to a polar charge order phase, in which a charge of a hole are disproportionated in each dimer in a specific direction, like this. If such an instability exists, the terahertz electric field may induce a transition from Mott insulator to polar charge order. Here I will show the result of this compound. To direct the polarization, we use the second harmonic generation. By a terahertz electric field, and second harmonic signals rises up following the square of the electric field, suggesting that a polar charge order state is produced. This second harmonic signal does not decrease by a reverse electric field at this time, and it remains after the electric field diminishes in this time region. This indicates that this polar charge order state is a metastable state. The detailed analysis of the transient reflectivity changes reveals that this polar charge order state is stabilized by the molecular displacement. Let me skip the details here. Okay, this is the summary of the second part. I'd like to emphasize that a terahertz electric field pulse is a powerful source to melt an ordered state, as observed in the Mott insulator to metal transition, and also to create more ordered state or a lower symmetry state, as observed in the Mott insulator to polar charge order transition. Next, I will discuss the Floquet state formed by a mid-infrared electric field. By using a mid-infrared pulse, it is possible to apply a higher electric field, typically 10 megavolts per centimeter, and also to resonantly excite molecular and lattice vibrations. In general, a mid-infrared pulse is obtained as multi-cycle pulse. So, using a probe pulse with a time width shorter than 10 femseconds, we can perform sub-cycle spectroscopy. These features of mid-infrared pulses enable to create novel electronic states such as Floquet state and investigate related electronic state changes. Before going to the result, I'd like to briefly explain a Floquet picture. Under light electric field that varies with frequency omega, new levels are created around the original level at intervals of h bar omega, as shown here. This was explained in yesterday's talk, but I would like to repeat it briefly here. The time evolution of the system is described by this Schrödinger equation. The Floquet theorem shows that if the Hamiltonian has a period t equal to pi over omega, as the solution is a product of the at rest state having a period t and the phase factor oscillating with epsilon alpha over h bar. This epsilon alpha is Floquet pseudo energy. The Fourier series expansions of Hamiltonian and this rest state are shown here. This phi alpha n is n photon rest state, which is n h bar omega apart from the original state. By substituting these into the Schrödinger equation, it can be converted to time-independent eigenvalue problem for Floquet Hamiltonian HF, which yields the eigenstate consisting of n photon rest state, as shown here. Now we can discuss the photon rest Floquet state inverting Mott insulators. The early studies of third harmonic generation and electroreflectance spectroscopy demonstrated that 1D Mott insulators show large third-order optical nonlinearity characterized by chi3. The chi3 values are much larger than those in good nonlinear optical materials of 1D Mott insulators. This enhancement of chi3 originated from the unique feature of the excited state. The lowest excited state in 1D Mott insulators consists of electron excitation to the other side like this. More precisely, the one photon allowed extrinsic state with odd parity 1 and one photon forbidden extrinsic state with even parity 2 are formed by the out of phase and in phase combinations of leftward and rightward excitations. The third order nonlinear optical response can be explained by the three-level model, which considers these two excited states and the ground state 0. In this model, chi3 is proportional to the square of the dipole moment 0x1 and 1x2. These two excited states are almost degenerate and have similar wave functions except for their phases. So, the dipole moment 1x2 between these two states becomes very, very large and enhances chi3. Such a large optical nonlinearity makes us expect to observe clearly photon-dressed Flock state. The studied material is another typical 1D Mott insulator, that is chlorine-rich nickel-chain compound. In the absorption spectrum, the sharp peak due to the auto parity exciton is observed at 1.95 eV, and the even parity state is located just above the auto parity state. We performed the mid-IR pump visible subcycle probe spectroscopy in a reflection configuration. This is the temporal profile of a probe pulse, and this is its spectrum, which covers the wide energy range around the auto parity state and the even parity state. By a mid-infrared electric field, a large reflectivity change with the rapid oscillations is observed near the absorption peak. A low frequency reflectivity change shown by the green line exceeds 30%, and oscillatory component extracted here has twice the mid-IR frequency, like this. This figure shows the reflectivity changes for various probe energies. From this data, we can extract the spectra of low frequency component and oscillation amplitude and oscillation phases, as shown here. These spectra should reflect the formation of Flock states. Here, I will explain the result qualitatively. By the mid-infrared electric field, the n-photon sidebands are created around the original auto parity and even parity state. When, the solid lines show the one photon allowed state. When a broadband probe pulse is incident here, the original transition to the one photon allowed state shown here shifts and loses its intensity in this state. In addition, the transitions to the one photon allowed sideband shown here gain intensity. These responses should be reflected by this spectrum of low frequency component. At the same time, various scattering processes associated with n-photon sidebands occur as shown by the purple lines, and interfere with the linear optical responses shown by the blue lines. In this case, the phases of scattering light change by plus minus 2 omega tau, where tau is the delay time of the probe pulse. This causes an oscillation with twice the mid-IR frequency. Considering this scheme and assuming the n-photon sideband as shown by the vertical lines, these three spectra are almost reproduced as shown by the solid lines. This demonstrates that the photon-dressed Flock state is homed in this compound. Okay, using strong optical nonlinearity in 1D Mott insulators, we can demonstrate a new type of terahertz nonlinear optics, that is phase and amplitude controllable terahertz radiation. The strategy of this study is summarized here. When OT parity and EV parity excitons are simultaneously excited using the two-color excitations resonant to the OT and EV excitonic state, a terahertz pulse having a difference frequency between two excitonic states can be generated via their interferences. The magnitude of this terahertz pulse is determined by the dipole moment between these two excitonic states, so we can expect strong terahertz radiation. This is a demonstration in a 1D Mott insulator of bromine-rich nickel compound, which have the largest chi3 among 1D Mott insulators. By adjusting the creation time difference of the two excitonic states with an attosecond accuracy, both amplitude and phase of the radiated terahertz pulse can be widely controlled. In this case, only the amplitude is changed, and in this case, with large delta t, the phase of the terahertz pulse can be controlled. Okay, finally, I'll briefly discuss the Honon-dressed Flock state. Note that the Flock state can also be formed by a modulation of electronic potentials by a Honon excitation. The studied material is potassium TCNQ. In this compound, an electron is transferred from potassium to TCNQ, and TCNQ anions are stacked along the A-axis. So this compound is also a high-field 1D Mott insulator. Below 395 K, TCNQ molecules are dimerized to form a spin singlet state in each dimer. This transition is considered a spin pulse transition. The strategy of our study is summarized here. This figure shows a totally symmetric intramolecular vibration, that is an AG mode. An AG mode is not infrared active in isolated molecules. However, an AG mode modulates the molecular orbital energy up and down like this. The out-of-phase vibration of AG mode induces intermolecular charge transfer synchronized with the vibration, and this mode becomes infrared active along this direction. Such an interaction between electrons and molecular vibrations is called electron-molecular vibration coupling. This out-of-phase AG mode will modulate charge and spin density in each dimer and create Honon-dressed Flock state. It hybridizes the antiferromagnetic ground state with non-magnetic state like this, and is expected to destabilize the spin pulse phase. Our purpose is to detect ultrafast dynamics of the decrease in the spin pulse dimerization by this vibrational excitation with mid-infrared pulse. This is the experimental condition. This figure shows the polarized reflectivity spectrum And this strong peak at 1 eV is the Mott transition, and sharp peaks below 0.2 eV are the out of phase edge mode vibrations. The band at 2 eV polarized perpendicular to the a-axis is the intramolecular transition from HOMO to SOMO in TCNQ. The intensity of this band reflects the charge and spin density in TCNQ molecule. So we measure the reflectivity change of this band. This is the electric field waveform of the mid-infrared pulse, and this is its spectrum. The mid-infrared pulse excites this edge mode 1. The probe pulse covers this intermolecular transition band, and time width is 7 femtoseconds. So we can perform the subcycle spectroscopy. The time evolutions of the reflectivity change by the mid-infrared excitation is shown here. To analyze this signal, we separated the high frequency component and low frequency component using Fourier filters. The signal includes 3 characteristic responses. The first one is a high frequency oscillation with a period of 14 femtoseconds. The second one is a slow oscillation with the time scale of 200 femtoseconds. The third one is the long-lived decrease of the reflectivity. First, I will discuss the high frequency oscillation. Its Fourier power spectrum shows 2 oscillations. The lower panel shows the Raman spectrum, and the upper panel shows the absorption spectrum. Its horizontal scale is half of the scale in the lower 2 panels. For the lower frequency oscillation, a Raman band with the same frequency is observed like this. So this oscillation can be assigned to this Raman band, Raman mode, excited by 2 photon absorption processes. The frequency of this oscillation is twice the frequency of this edge mode 1. This oscillation can be assigned to the out of phase edge mode 1 vibration. The state of electron transfer to the right and to the left are equivalent like this. Therefore, an oscillation of twice the frequency of edge mode 1 appears in the reflectivity changes. This 2 omega 1 oscillation can be considered to originate from phonon-dressed Flock state. Okay, this is, I skip the details. Next, I will discuss the low frequency component reflecting the destabilization of the spin-pile space. Its Fourier power spectrum is shown here. 4 oscillations are observed like this, and by comparing these oscillations with the Raman spectrum, these 3 oscillations, B, C, and D, can be related to these 3 Raman modes, which are illustrated here. All these Raman modes modulate the dimerization. This result suggests that the out of phase edge mode vibration, this high frequency oscillation, destabilizes the spin-pile space, and oscillations of B to D, very slow oscillation corresponding to the release of the dimerization, are generated via the displaced excitation mechanism. The results also suggest that the long-lived decrease of the reflectivity is due to the reduction in the averaged dynamic molecular displacement. Note that during the presence of the out-of-phase edge mode vibration, like this, the spin pulse dimerization should remain destabilized for a long time. So that is the important point. Okay, this is a summary of the third part. The application one is to inherit electric field with a frequency omega on a 1D Mott insulator of nickel chlorine chain compound induces large reflectivity changes accompanied with a high frequency oscillation with 2 omega. Analysis based on the third order optical nonlinearity demonstrated that the photon-dressed flock state formed. Furthermore, the charge and spin density modulations by an out-of-phase edge mode vibration in the spin pulse phase of potassium TCNQ hybridizes the anti-ferromagnetic ground state and non-magnetic state. It creates phonon-dressed flock state and destabilizes the spin pulse phase. This is a new type of flock engineering. Okay, in summary, we introduced the responses of far-field Mott insulators to light and electric field. We have discussed the ultrafast dynamics of charge and spins in photoinduced insulator to metal transitions, a new type of terahertz nonlinear optics, terahertz field-induced quantum tunneling and charge transfer, giving rise to the phase transition, and detections of flock state and flock engineering. As a final remark, the experimental techniques and approaches presented here may be applied to various types of correlated electron materials to derive novel optical responses. Okay, this is my collaborators. Second transient spectroscopy and analysis have been performed. The member of my laboratory and sample preparations have been supported by these professors. And we also thank the theoreticians for collaborations and enlightening discussions. That's all. Thank you very much.